Okay, so good morning everyone. Today's lab is about building a convolutional neural network and seeing how it compares to last lab's neural network, which is just a standard multi-layer perceptron, right? So we'll be building a CNN using PyTorch, and CNN is a convolutional neural network, and the reason we use it for image data is because it maintains the spatial nature of an image, right? Now, when you look at an image, you need to understand that what the last neural network was doing, it was considering each part of the image as a flat pixel line, right? It didn't care about the location of the pixels themselves. If we like jumbled all the pixels in the MNIST data setup the same way, of course, if we jumbled all the images up, jumbled all the pixels up and ran it through a standard neural network, it would achieve the exact same accuracy as our last model. Why? Because it doesn't care about the position of the images themselves, of the pixels in the image themselves. So to rectify that, we come up with something called a convolutional neural network, which uses a few things to sort of maintain the spatial integrity of the image itself. So we're creating features, or we're looking at features by using something called convolutions and convolutional kernels and pooling. So as I'm sure you've seen in the class lectures, a convolutional kernel is essentially a matrix filter which is applied to an image over parts. So if you can see on your screen right now, this is the kernel which is multiplied by this image, and you will get an output of a single number, right? Um, so it's a multiplication which is element by element. It's not a standard matrix multiplication of row by column. I hope everyone's clear with this. Um, Similarly, if you look at another, so this quality is really bad, so don't care about the numbers themselves. But if let's say I had an input image of size 7 by 7 and I had a filter of 3 by 3, then I would have an output of 5 by 5. And you can sort of see this one at a time. So if I have an image which is here, right, the next filtering will start at the next um, column length. This is what happens when you have a stride of one. We'll come to what happens when you have different strides later. Um, and a good example and a good way to visualize why convolutions really work is this one. So as you can see, if you look at the image itself, it's an edge, right? It's a 10 by 10 by 10. It has three columns of with pixel value 10 and three with pixel value 0, which means that there is going to be an edge at this middle point. So to figure out how we've multiplied it by by this matrix, and as you can see, it can sort of figure out that this middle part has an edge. It's looking at this part and saying that there is some feature here which needs to be analyzed. And as we can see, there is an edge. So in the middle area, there is an edge that can be seen. So this is a little bit about convolutions. Similarly, max pooling. I don't have an example. Let me just do that. Similarly, max pooling is for essentially downsampling the image. So let's say I have an n by n image and I want to convert it to an n by 2 image, let's say hypothetically. So I can use something called a pooling um, algorithm, not really an algorithm. Um, so this is a pool with a stride of 2. With a stride of 2 means that it shifts by um, two columns every time it moves, or for the next operation, right? So here, this is the first operation, then it moves by 2, and then this is the second operation. If this had a stride of 1, the output matrix would have been a 3 by 3 matrix. um, so that there are a few types of max pooling. There are a few types of pooling. This is a max pooling which takes the largest value of the numbers in the matrix it's sampling. There is something called average pooling, which takes the average of this, and there is one sec. There is min pooling, which takes the least value of the batch which is selected, or the operation that's conducted. So in an average pool, this would be a 28, 24, I think it would be 13. And the min pooling, this output would be an 8 for the red matrix. With that out of the way, so today's agenda is going to be looking at convolution, looking at CNNs and building a CNN first. Then we'll be looking at something called fine tuning, where we take a pre-trained model on a very large data set or on a relevant data set, and we pre-train the last few layers for our purposes um, to match the kind of data set that we want. Um, and yeah, that's sort of all we'll be hoping to cover today. So similar to last time, we'll start by importing what we need. So import torch vision. ISMP. So we'll be building it again on MNIST because it's just faster to train. There's no other reason. You can do this for a lot of other um, data sets as well if you'd like to try and see how accuracy turns out there. MNIST is just a very good standard you can use. So this was all covered in the last lab as well, where we imported the MNIST data set and then used it directly. So in the last lab, if you remember, we were flattening our images into 1 comma 784, which is one row 784 values. The reason we will not be doing that now is because we are not training a single vector. We're training an image which is a 2 by 2 value. The 2 by 2 vector that we'll be training.
Hello.
Hi.
Could you scroll up a bit?
Yeah, sure. So it is imported packages and
I'm
downloaded
getting
libraries.
the error that MNIST is not defined.
Sorry.
Right. Sorry.
Um, I hope it's clear. So I forgot to import a couple more things that we will be needing. This is all. This is everything that had still been covered in the last lecture. So I hope everybody is following so far. Now we'll be building the model itself. So the CNN model. This time we won't be initializing weights. We'll see what happens when we don't initialize weights at all. Um, the model will still learn, so it doesn't make a big difference. Now, when the convolution layers here, I'll come to what they mean in a little bit. I'll finish writing them out first. So our convolution layer, the one I showed you previously on the during using the image, is called con2D in PyTorch. It got a few parameters that you need to take care of. But we'll come to what they mean in a minute. So if you remember the matrix sizes we were seeing, so we saw 3 by 3 matrices and a couple others, right? Those are essentially the matrices that we're multiplying by the kernels. The kernel size determines that. So whether it's a 5 by 5 matrix or a 3 by 3 matrix, um, and stride of one, again, like I showed you during the coding example, is essentially that it moves by one column every time it moves. So if let's say I have a 4 by 4 image and a stride of three and a stride of one with a 3 by 3 kernel, my output will be a 2 by 2 matrix. I hope everybody is able to visualize that.
Could you just repeat that? What will be, how does the output change when the stride is changed?
So let's say I have a 4 by 4 matrix with a 3 by 3 kernel and a stride of one. The output will be a 2 by 2 matrix, right? Now with a stride
Yeah.
of two, that's not possible in the example I've given.
Yeah, got it.
Correct? Yeah. Coming back to pooling, so there were three types of pooling that I told you about, and the difference between each of those is that max pooling retains the most important characteristics of the area that it's sampling, right? Um, and that's important because you sort of want the maximum, you sort of want the most important features in a given area, unless you're looking for areas that are darker, right? In that case, you want min pooling. Similarly, average pooling is probably for like a direct downsampling of the image by a certain amount if you want it. Again, here we'll be looking at um, we'll have to create a linear model. We'll have to create a fully connected linear model as is because what we've essentially created after the convolutions is a feature map. We haven't really and we have to map those features to create some sort of um, to create some sort of in like a linear in like a in n by n dimensional space. you need to map that feature map to an output, and that's done best by a linear fully connected layer.
Excuse me.
Yeah.
For the first linear layer, how did we get the input size as 4x4x10, as in 4
Um,
10?
so your image size is 28 by 28. Try looking at what happens to the image size.
Okay, after the first two convolution layers, you mean?
Yeah.
Okay. Yeah.
Now, you can't really know without just the image size, because the model that we're building isn't just with the convolutions. There are going to be poolings at every layer. So I'll show you the forward function first, and you'll be able to figure out exactly what the image size is going to look like. So again, the ReLU is the activation function here, which will be applied after the convolution. Um, the activation function remains exactly the same as the last time, where it's a max of 0 comma x. It's just there to induce nonlinearity. Again, we'll be studying more in depth in the lectures. Now, take a minute to sort of go through the forward pass function and see whether it makes sense to you.
In the forward pass, for the second convolution railway function, it will be con2, right? Instead of con2d. Like the name of our convolution
Yeah,
is
yeah,
con2.
my bad, typo.
Yeah.
I think you'll also have to pass x to self.pool, right, in the forward function.
Well, yeah, again, yeah. Self.lint2 will also need an X. I don't think I missed anything this time.
Hello.
Yeah,
Uh, in the first convolutional layer, the input is of the size 28 by 28, right?
correct.
So the output would be 24 by 24.
Yes,
And in the second layer, it becomes 20 by 20.
right.
The third layer, it becomes 10 by 10.
By here, right?
Uh, no, by this max pool, by max pooling.
Oh no, no. So you follow the order in the forward function here,
Oh,
not the order
oh,
here. So this is the function that you have like you have defined. So what a conv1 function is, it's this. What a pool function is this. But
all
the
right.
order you'll be following in your forward pass is like these, in this order.
Okay, so then first from 28 by 28, it becomes 24 by 24, and then it
Right,
gets pooled. So
right,
after pooling, its size would be halved. No?
correct,
So then it would become 12 by 12.
right.
And then, okay, then ReLU. Oh, ReLU on, okay, so then again it would be 10, 8 by 8.
Yeah,
Uh, 8 by 8, say it would become 4 by 4.
correct.
And then it is flattened, alright. And then linear 1. 8 by 8.
In case
But
the
then,
number of channels don't aren't making sense, go through this image. Now ignore the fact that there are three channels here. Okay.
hmm,
Just imagine this to be one, and now try to look at the convolutions. This is nearly the same architecture as what we're following. Like the first four parts at least, not the rest of it. It's a much deeper network.
what is S here?
Oh,
The
it's
S.
stride length.
Okay.
So they've written same here. I'll explain what that is in a minute here. But first, make sure the number of channels sort of makes sense to you, at least from an visualization perspective. You should be able to see why it's getting why this is why the number of channels are increasing.
What is the kernel size here for convolutional 1?
In 11 by 11 here.
Okay. Okay.
The conv1, this is the result of conv1. This is the operation conv1. This is max pool, which is this operation. Conv2, this operation. Max pool, this operation.
Excuse me.
Yeah,
In the forward pass for the last linear error, we have just written self.lin2, right?
yeah. There will be no activation for the last layer.
Uh, okay. But then, like, don't we use softmax, uh, like in the last layer?
Uh, we one sec. Not necessarily. So you can still
Okay, as in, like, if we don't use, we'll get all the probabilities, and if we use softmax, we'll get the
yeah,
one with the
we'll use
most.
cross entropy loss, which will be used to train. We don't necessarily need to use a softmax here.
All right.
So you see while we write the train function and the test, while we write the train function, how we're using. So you can use a softmax or a sigmoid there also. You will eventually need to introduce some sort of loss function, but not here. Not necessarily here.
What is the reasoning for using such a structure of the network? Like why two layers and then why two more layers linear?
So this is based on past deep learning structures. So we tried out a bunch of different things, and this one worked best. There is a deeper understanding that you can go into when you when you start reading literature. Um, but the basic structure will always remain the same. There will be convolutional layers, there will be max pooling layers, and there will have to be fully connected layers at the end. Why this exact kernel size and this exact stride? I'm not very sure myself, but I generally tend to follow what past successful deep learning frameworks have followed for similar image types,
Okay.
if that makes sense. Okay, so moving on from here, now we'll prepare our. We'll see what this does now. So torch.unsqueeze, so I'll show you the documentation for torch.unsqueeze. It'll return a new dimension, a new tensor with the dimension of size 1 inserted at the given position. So let's say I introduce torch.unsqueeze x squared 0. So we'll sort of wrap this around with another, um, they'll wrap this in as an element of another tuple. Why we're doing that? Again, you'll see in the training loop why exactly we're doing that. Um, but like if I apply this same operation tortured unsqueeze x comma 0 twice, this entire thing will be the element of another tuple which will be here. So there'll be three opening arrow brackets and three closing arrow brackets. So as you can see, the training, like the train X size now, which is also going to be the same for the other two, is now 50,000, which is the number of images, times 1, which is the initial number of channels, times 28 by 28. So this is the image, like this is the 2D side of the image, and this is the 3D depth of the image. Now, if you had an RGB image, which we will deal with later, this will be 3, because you will have R, G, and B as 3 different layers. The sum of the 3 layers together will sort of be the final image that you will be dealing with. And we're just sending them to CUDA because they're faster to train that way. For Colab users, again, please note that um, the runtime you're connected to needs to have GPU enabled. Otherwise, this will throw an error. Never mind. I don't think I've connected to our runtime, which is yeah. We'll actually change that. So uh, another one. Right. So when we switch this to GPU, this will work now. I think we have to run all now. So this is because the runtime changed. So the data that was stored in, let's say, a variable train underscore x is now not there anymore because the CPU has changed. Right. So we're good because now these are all shifted to CUDA without throwing an error. Dot CUDA can also, as you can see, be applied to an object like an object of an object of a model. The CNN model here is so we're creating an instance of the CNN model object, and we can push the entire thing to CUDA in one go instead of having to shift individual parameters there. Again, very similar thing to last time. We'll be creating a batch size. 128 is good because it matches memory. According to literature, I'm not sure how that works. That's a systems programming thing. Number of batches or train epoch. And that is going to be the number of images divided by the batch size. Number of batches validation. Same thing, number of images in the validation set. Divided by the batch size. So now we'll be importing the optimizer. Optim as optim. Last time we used stochastic gradient descent. You can also use an Adam optimizer. Um, and if these will be covered in the theory lectures, I'm not sure. However, the accuracy function will be exactly the same as last time. In fact, I'm just going to copy it from the last lab sheet. And our optimizer is going to be now today we're going to see a couple interesting things. We'll be see most of them later on when we're doing fine tuning, but just wanted to introduce them now. Um, there is a parameter here called momentum, which I can set. I think, yeah, which I can set to be, let's say, 0.5. And what momentum essentially does is that it speeds up training and prevents local minimas. If you want to look at the function itself, it's essentially the current gradient plus the change in the previous gradient into the momentum factor, in this case, which is 0.5. So the higher the momentum factor, the more um, momentum it essentially has. So if I had to show you a graph on momentum, I don't have it open, so I'll just open it. Okay, I can't find. Yeah, here. So is my screen visible? Okay, I think it is visible. So here's an error function with momentum. So here's a great backdrop with momentum, which is the one in like dark blue, the non-dashed ones. Um, and the difference is that it's sort of smoother. Now there again, not the greatest graph you can look at, but if you have the time, I'd recommend you go through a lot of the other graphs which are on momentum. You don't necessarily need momentum for training. We didn't use it last time, but it's generally a good practice to. Okay, wait, my screen isn't shared. My bad. Is my screen visible now?
Yes.
Yeah. Um, yeah. So the forward pass, so the training function remains nearly exactly the same as last time. I think it remains exactly the same. Uh, because you have to do the same set of things, right? You have to start with a forward pass. You do a backward pass, and then you do a weight upgrade. It's not any different than last time. Right? So we can actually copy the exact same thing as last time because we wrote it in a very generalized way. We can't just do that. So if you go back to your lab sheet and copy, so if anyone's following along and doing this alongside, I'd recommend that you actually copy the exact same thing from last time and try it again. I will not. I don't think I'll write it down. So I'll also just copy it from the last lab sheet. I'll go through it once just to make sure we're all on the same page. But it should work. So epoch loss, which is the loss at each epoch. An epoch is one iteration where all training examples are covered. All training examples have been have gone through the model at least once, or actually just once. No, one epoch is just once. The losses at epoch, we've created a list for this so that we can make sure that we know at each epoch what is the loss, so that we can plot a graph for it later on. Then we have training accuracies again for each epoch, what are the accuracies? For each epoch, what are the validation accuracies? So for epoch in range number of epochs, we have defined the number of epochs to be 20 previously. You can change the number, play around hyperparameters. You can sort of look at what point it starts overfitting. Um, and that's sort of the maximum number of epochs you need. Now there is something which I can remember is called automatic stop. I've used it more on other machine learning applications such as random forest, but I believe it also exists in PyTorch. I'm not very sure about this, however. So that essentially stops when your model is sort of on the cusp of overfitting. When it's like fitting well versus just overfitting, it stops training the model further. Similarly, so model.train, as you remember, will enable gradients for all tensors. Model.eval will stop updating weights and will stop, and the torch.nograd will be false. So torch.grad will be false, not torch.nograd. So let's see if this runs. The exact same code runs. Right. So as you can see, it works, and the training accuracy and validation accuracy are also working fine. Okay, so as you can see, we're sort of at a good fit in this situation. Um, I don't think we're necessarily overfitting here because the training accuracy has increased without decrease in validation accuracy. Um, that's generally the easiest metric to check for overfitting. So yeah, if you also remember from the last lab sheet, the sheet that you were provided, the code didn't work during the lab for some reason. I have gone through it; it works now. So the lab sheet worked perfectly. We tested that out later on. Um, so as you can see, the validation accuracy here is a lot higher than the ML is not a lot higher, but it's still significantly higher than the MLP we had built last time. And what's interesting to note is that if we look at the number of parameters here, which I will just show you in a minute, you will see that the um, number of parameters are far fewer than the last model. In the lab sheet, the last lab sheet for the MLP, it came out to be about 49,000. Here you will see that it comes out to about about 20,000 or so parameters, which means that it's doing a better job with lesser parameters. Basically, it's showing you that the spatial data that it's trying to recognize is what is why this is happening. So it requires not required. Yep. What parameters? Oh, underscore parameters only. Oh, what is this here? Oh, p dot size. So as you can see, about 19,880 parameters, which is a little over one third which we needed for the MLP to have close to 90% accuracy, and here we got 96% accuracy. So CNNs are far superior for image data as compared to a standard MLP. And as we had discussed previously, they don't suffer from the same problem um, as the ones we had discussed, which was essentially not being able to recognize spatial data. So again, if I jumble up an MNIST in the same, or if I jumble up MNIST pixels in the same order for every image, my MLP will still work, but my CNN will give me will give me a pathetic accuracy because it's not able to recognize any patterns in the image in the spatial nature of the image itself. So you can sort of look at the visualizations during the lab sheet. That is not an issue. This is going to run the accuracy function. Should be similar to the validation accuracy.
Yeah, I had a doubt in the function, the forward pass basically.
Sure.
So
We are, yeah. Sure.
Yeah, so the thing is that after the max pooling occurs, we have a
Right.
4 by 4 matrix, right? Let's say
Right.
4 by 4 tensor. So
Yeah.
why have you taken the input features as when you flatten it, you get a 16, you get 16, I'm assuming you get 16 features from the image, right?
Okay.
So why are the input features mentioned as 4 into 4 into 10? Like,
Because they're not. So they're 4 by 4 in a 2D sense, but there are 10 channels behind it. So if you go here, you can see that the output number of channels are 10.
okay.
I'll show you the Alex the image I had shown again, just to give you an understanding of why that's happening.
So like, is there a reason why you're making the channels? Because like,
Uh,
what if I do it without the output channel? If I keep the output channels as one, do you think that will make a difference?
let's see what happens. Let's see what happens. This is now going to be 4 by 4, right? So the output features will leave as 10, and then we input 10 output 10. Make sense? Yep. We'll have to start again because the unsqueeze will give an error. So the reason we're increasing channels basically is that, so this is also giving you a decent accuracy, right? If you can see, it's still 81%. It's not a terrible drop. So if I probably train this for 40 epochs or 50 epochs, let's see what happens if we train for 50 epochs. But essentially, you're downsampling data as you move forward. So you can afford to have more channels because you can keep the number of, you can still increase the number of parameters because your 2D images is pretty low. So this is 20 plus whatever you see. So this is still going to converge to a lower area because now the number of spaces you can create are fewer, as in the number of feature maps you are generating are lesser. Um, so this will definitely not converge to a 96%. But essentially what happens is when you increase the number of channels, you're able to create a larger n by n dimensional space or a larger feature space for you to like map your data distribution to. What a neural network is essentially trying to do, it is trying to match the data distribution of the training data and see how similar the test data is to it, right? Ideally the test data will have an exactly, so in an ideal world the test data will have the exact same distribution, data distribution as the training data. And if your data is linearly separable, an MLP will be able to converge perfectly on it. For CNNs, that's not possible because the data distribution is slightly flawed. So even your feature generation is not going to be exact, which is why you cannot. I don't think it's theoretically possible to have 100% accuracy on it. But the reason you increase the number of channels is to increase the space that you're working with while still mapping features to something. So you're increasing the number of features you're mapping essentially. Does this make sense?
Yeah, it makes sense now.
Yeah. So I'll change this back. Just a second. So if you want, you can try this out with like 20 channels as well. So the number of parameters in your model will increase. So it again might take a few more epochs to train, but should work perfectly fine, I think. The reason I'm having to download the dataset and do this entire process again is because the torch.unsqueeze function is waiting here, which is a terrible place to put it. Because every time I have to make a change to the model, I sort of go through here anyway. Ideally, I will put this here after or just after the training data splits have taken place, so that I don't have to go through the entire process again. Yeah, so I was writing the get. Okay, what is the problem here? I don't think I have made a change. Yeah, I haven't multiplied that by 4 by 10. Should work fine now. So you can see here, this is actually converging to a very high accuracy. Like after 50 epochs, it's converging to nearly 98%, 99% to 98% validation. So if you also see the curve sort of flattened out after the 25th epoch, or not the 25th epoch, but after like the 40th epoch, not a lot of change in terms of your validation accuracy. That actually happened over the 30 epoch. 98.0 and 98.17 is not a massive difference, but as you can see, the validation accuracy is like practically stabilized, which means it's almost definitely not going to get better from here. In your lab sheet, you will be oh, in the lab sheet you will also have plotting tools. So you will be using matplotlib and a couple other libraries to sort of see how this graph is turning out to be. So ideally, you should be trying out a different number of epochs, maybe trying out a different model to see how it works. But again, the structure remains exactly the same. So this is essentially the neural network, a standard CNN network. Now we'll be looking at something called fine tuning. Lab sheet been shared? This lab sheet has not been shared yet. Last week's lab sheet was uploaded to the website. This lab sheet will be shared with you tomorrow. Tomorrow or today EOD. I'm not sure when exactly, but it will be done. We'll put it on the WhatsApp group. And it has been shared. So now we'll be looking at something called fine tuning. So as you can see, neural networks are pretty complicated, are pretty computationally expensive to train, right? Just a 28 by 28 network took a decent amount of time. It wasn't instantaneous like certain algorithms or models are. Linear regression in that regard is pretty fast, but neural networks by nature of their complexity and the number of parameters they have are not. So how do you deal with something like this, right? So there's a concept of transfer learning which is used here. And in that, we essentially take a pre-trained model, a model which has been trained on either a data set that's very similar to the data we want to train on, which has a very similar distribution, or is able to generate the requisite feature maps that we want. So as we saw in the images previously, right, there are certain types of convolutions which can like detect edges. So if you wanted to detect a virtual edge, there's an exact type of convolution for that. If you wanted to detect a horizontal edge, there's an exact type of convolutional kernel for that. Similarly, if you want to detect edges which are like non-linear or sort of not in the exact way that was present in the examples I had shown, um, the during backward propagation, it will sort of recognize the fact that there should have been an edge here, but it's not able to recognize it because of the weights being the way they are presently. It will update it and it sort of will start to create a feature map where it will start recognizing the edge slowly. Once that takes place, you can sort of see that the same edge will have a very similar feature map regardless of the kind of image you put into it, because it's essentially just edge detection. Does this make sense to everyone? Are there any doubts? No. Okay. So what we'll be doing here is that we'll take a model which is very large. So ResNet 50 has 50 layers, right? Sort of in the name. And it's one of like the most well-known models out there. If you go through any papers, you'll see that ResNet is probably like the most famous model there. And there is a very large image set called ImageNet, which was used for a competition. I think it was called ILS-RVC. I'll just check the full name and type it down here. Which was the ImageNet Large Scale Visual Recognition Challenge. So I'll just type that out here, fine tuning, and I'll add another piece of text, which is ILS-RVC. In case any one of you are interested, you'll find a lot of the standard deep learning frameworks have actually started here. AlexNet and Linet were initially, I think both of them won ILS-RVC in their respective years. ResNet, I think, also either won or placed in the top three or something. So it's a very, very large. So ImageNet is a very, very large image data set which consists of 1,000 classes and close to 1 million images, if I'm not wrong. Which means that any model trained on something this large will definitely be able to have at least the basic feature maps in place, where edge detection can take place, and just a general set of feature maps will definitely be there. So we want to leverage these feature maps to not have to train the entire model from scratch. Now, let's say we're using something like an MNIST. We won't be using an MNIST here. I'll come to that later. But let's say we're using something like an MNIST, which has only about 50,000 images. Now, 50,000 images doesn't even compare to the million images that ImageNet has, right? And if ResNet is able to fit, if a 50-layer model is able to fit perfectly to, let's say, 1 million images, it's most likely going to underfit in 50,000 images. The standard rule of thumb is that the number of data points should be close to 10 times the number of model parameters, roughly, or 3 or 5 times amount is also generally sufficient. Now, in this situation, it's not even close, right? The 50-layer model is going to have far, far more many parameters. I think it's close to 15 or 20 million parameters, probably more. So as you can see, you sort of have to figure out a solution to that. So in this situation, what we're going to do is we're going to use the pre-existing feature maps that ResNet already has, and we're not going to perform backpropagation on those. And instead, we're going to create two more fully connected layers, or freeze the last two fully connected layers. Oh, sorry, we're going to freeze the rest of the model where no backpropagation will take place, no weight update will take place. Only the last two layers, which we will use for classification, for for the features that have been generated, will be used to create the outputs and classify. Are there any doubts? No. Okay, moving forward. So we'll be using a data set called Opera because it has a higher image quality than MNIST. The reason why that's important is because ResNet's input is 224 by 224 pixels, and an MNIST is 28 by 28. So you really can't use it there. You have to do a lot of sampling if you absolutely want to do it, or you'll have to sort of create a model similar to ResNet or input images, or you just have to compress ResNet by a lot. So this is a PyTorch data that you can download. I'm copying this from from their website. Um, this is part of the tutorial. This will be part of the lab sheet, and the link will also be shared. You can directly look at it from there. So this is a lot of, so what I'll be writing now is just a lot of like coding it out. There's no real concepts to this, and if there are any concepts, we'll be covering them in the next lab. Right. So as we had discussed, right, the model we'll be using is a pre-trained ResNet. We'll use use a ResNet 18 actually. You don't need a ResNet 50. But again, 18 layer model is still significantly more heavy than. So here what we're doing is we're setting all the parameters in the model. Why is this one? Yeah. And the setting there requires grad to false, which means that during backpropagation, no weights will be updated for these parameters, which is all the parameters in the model. Um, and model.call. Um, I see the chat is there. Okay, attendance mark, right? My bad. So now what we're doing is we're we're creating like more fully connected layers. Actually, just one more fully connected layer, which we're doing so that we are able to classify based on our data set. So this is called model fine tuning, right? Model underscore. Uh, then we use ingredients. Here we'll use momentum. Uh, why? No real reason. You can sort of see what values of momentum work for you. You can actually go through the theory and figure out whether you need it for your purposes or not. It shouldn't technically affect whether your model converges or not, given like enough different seeds. The reason for that is that uh, your model still would be able to map it, would be able to map any function to a requisite linear in a linear space. Momentum sort of just aids with the training process. You don't have to use different seeds or sort of worry about different seeds. Um, there is also something called a learning rate decayer or a scheduler, which will decrease your learning rate for every like for every few epochs. This is done specifically for fine tuning. Generally done for fine tuning. You can do this for other purposes also. Um, I don't think we'll be doing that here though. Never mind. So we're running a little short. Are we running short on time? Not really. So no worries. So you can again use the same training loop as we had before with the one here which we had done with the batch size. I don't necessarily want to do that here. Is the reason for that is because I want to have a gradient of it every single time, which again you can do there. But this is a very generalized function that I'm writing now. This is going to help you sort of. So this is far more reusable than the last one. Um, so we'll just write this out now. This is going to help us in future labs. Have I imported type? I have not. Now, um, an interesting question could be that if feature maps are already being generated in a pre-trained model, why don't we just train the whole thing again? Because the feature maps should remain relatively the same for each image, right? And that's a fair question because they will remain nearly the same or exactly the same for each image because it's the feature maps would remain nearly the same. The reason why we're not doing it is because the change in feature maps, if there even if there is a change in the feature maps at certain convolutions or at certain layers, they won't be very significant because the number of images that the reason why we're doing fine tuning and not training the full model is because we don't have a lot of data. So the gradient updates are the weight updates are going to be very, very small. So you're actually doing a lot more matrix calculations, which are very computationally expensive, um, simply because you sort of like wanted to, but there's no real reason to because as we can see, ImageNet is pretty large. For other fine tuning and transfer learning purposes, you use data sets that are sort of similar to your task at hand. So if I was doing, let's say, facial recognition, I wouldn't necessarily use ImageNet because ImageNet consists of classes that are significantly different. I would probably use a model pre-trained on like images from faces or facial or other facial recognition data sets. Right. So each epoch has a training and validation phase, right? So earlier we used to sort of just run it into different loops. Here we're making a slightly better function, in my opinion. Again, no real difference in terms of training ability. It will still converge. So we haven't written the data loaders yet. I will, for the purposes of today's lab, I will simply write the code out. We'll be covering what a data, how a data loader works exactly in the next lab. We'll go into the nuances of that in the next lab. For now, just yeah, this is going to throw in error because we haven't written the code yet. But for now, just assume that a data loader is used to upload a data set that is not already available on torch or datasets. into the um, into Colab or whatever you're working on. So if you're working on, let's say, a locally hosted Jupyter notebook, a data loader will upload it there. In there, you can actually use os.dir, but data loader still work. Okay, we don't need to do this. We can directly. I can't hear you. Could you repeat that, please? Okay, nobody's talking. My bad. Probably someone outside. Right. So here we can again optimize and got zero gradients. Now with dot set gradient. It's also covered in the last lab sheet where we sort of discussed why you need to switch from model.train to model.eval. Um, Same reason we don't want to update gradients unnecessarily. Yes. This is our backprop step. Right, this is not backprop, this is loss calculation. This is backprop. This is beta. Running loss and total loss. Loss dot item will give you the loss that it is just calculated. At every iteration, it will be set to zero again. So you can go to the documentation on that if you're on the loss function as a whole, not just the function, but how the code is written. Um, yeah, I think we're done with the loop now. No, so now we can calculate hypocrites. Just going to copy this. So this part is important. Um, you can sort of see that a lot of times the validation accuracy actually decreases over time, right? And you don't want to lose the, let's say, best case model that you had previously because you overtrained or had too many epochs. So one way to deal with this is to set checkpoints where in case, let's say, your computer crashes or something, the model weights are stored somewhere. Here we'll just directly copying best model which we have. I hope everybody knows the difference between a shallow copy and a deep copy.
Could you explain that difference between the shallow copy and the deep copy?
So a shallow copy creates a reference. So let's say let's say I'll just create a new code part here. So let's say I write a equal to torch dot linspace b, and then I say c equal to torch linspace b doesn't make sense. But 1 comma 10 comma 1. Right, c, and I just write c equal to a. Now here what's happened is it's created c is now pointing to the reference of a, or where a is stored. It's not a new memory location that's taking place. So this is an example of a shallow copy. When a deep copy takes place, so let's say I write copy dot deep copy of a. Now C is stored in an entirely new memory location, which is different from A's memory location, but it has the exact same contents of A. So if I just do C equal to A, and if I don't do copy dot deep copy here, so let's say I do C equal to A, I do this. If I make a change to A, C will be affected. Here, if I make a change to A, C will not be affected. It will remain the original contents of A which took place at this operation. Does that make sense?
Yes. Yes.
So then it's just a question of updating the best accuracy on the model parameters, not epoch loss, epoch accuracy. Right. So I'm just going to copy the from the lab sheet. This again will be shared with you in a bit. Just doing this for the sake of time, not very complicated. Um, if I haven't missed anything. Then it should be outside the yeah, and these should be here. Yeah, and in case this doesn't look the same as in your plan, then I'd say an indentation to two spaces instead of the usual four. In case someone thought it looks weird, it does. Right, this seems about right. I don't think there's an error. So I'll just write the data loader code out. Um, Again, don't have to worry about how it works. Not for now, we'll worry about that next session. So this is also a concept called data transformation. So what we end up doing is that we sort of do other things, right? We do random flips and random like crops resized to a certain amount. And the reason for us doing that is basically to sort of augment the data. Uh, why do we do data augmentation? We'll, so we sort of artificially increase the amount of like the data we have by like just let's say I have an image and I flip it over the over like the if I and I flip it horizontally. I essentially have another image because if I'm looking for a B is the same in both axes, right? I can flip it and it will still remain a B and my model is still supposed to recognize that, right? So it shouldn't, it will increase the amount of data that we have. And obviously with all things that are around, PyTorch also has the function for to do this. So start random resized curve. Now, as you can see here, we have to resize it to 224 by 224. The reason for that is the input to our model is 224 by 224, so we have to. Now, this will increase the amount of data that we have by creating random clips. The next part is interest. This is um, sort of interesting. The reason that I haven't written the code out to explain the values here, but if you go online and look at the Hymenoptera dataset, you'll find these values. Now, I'll explain this function in a second. I'll get the values out first. Right. So, does anyone remember what the formula Gaussian for a Gaussian distribution is, or what the um, characteristics or parameters of a Gaussian distribution are? Okay, so Gaussian distribution is a distribution over the norm, or is a normal distribution with mean equal to 0 and standard deviation equal to 1. Um, right. So here basically what we're doing is we're creating a distribution. So this is the mean across the first. So the 0.485 is the mean on the first channel. So we have done let's say a val minus uh, mean by standard deviation. Right? This is going to create a Gaussian distribution. It's going to mimic a Gaussian distribution for your data. Now you can, it's an exercise left to you to sort of calculate this mean value and the standard deviation from the image itself. Not a very difficult task, can be done in NumPy also, don't need PyTorch. And this is nearly exactly the same for test, except we don't have random resized crops, we have center crops. And for that, straightforward, we want the C documentation. And normalization remains exactly the same because it's the exact same data. I hope this is clear to everyone. You will go into data augmentation deeper in your lectures, I think. So after this, you are not expected to know or sort of like do this and have it now. We will cover this in depth in the next lab. You will also not be questioned on this during your testing. But for good practice, I would recommend that you should follow this. Try to follow it by now. this is the data loader function. It sort of does a lot of things for you automatically. Um, Useful. It will shuffle the data for you just to make sure that there is no pattern or gap, or like the train test data is not split in a manner which is like not beneficial to your model. So shuffling them is generally a good idea unless you sort of want to have a specific sort of transfer that you're looking at, or if you're looking at some sort of um, what's that called, some specific sort of transfers that you're looking at. But for most image type data, shuffling is generally a good idea. And the number of workers are essentially the number of processes it will do it because it's a very heavy process. I don't see the problem here. Yeah. And I think we're good to go. We are not. Yeah, this R is also probably capital.
While in the data transforms dictionary, the second key should be val, right?
Right?
Yeah,
Oh, right. I did copy it on
right.
forward. My bad. Um, and now we just write a short function to train it. So the model function. You can make them columns. And oops,
You have kept the batch size as 4 in the data loaders. Why?
Yeah,
I think you'll have to change that.
right. I wanted to go back and change that original one, but okay, we'll change this to 128 instead. Oh, we got a lot of values today. Input start size. What line is that? And dataset sizes. I don't think I have defined that up there. Never mind. Where is this problem? So it says we're doing backprop twice. Um, how do I use it? Oh dear, one sec. We'll have to sort of figure this out. Does anyone see the error? I'm not able to for some reason.
Maybe you can try running everything once again. Not sure if that will work.
Yeah.
Like, I think you'll have to reinitialize the loss function because it has some gradients accumulated on it once you ran it.
Yeah, that's right. Right. But we did reinitialize it this time. At some point, it's running again when it's not supposed to. Let me just go through torch dot set grab. That might be right. Oda order memory. Okay, interesting. Not the same error as before.
Maybe how to reduce the batch size, I guess, because it's 128 images.
And not set that set. 4. I think I'll just directly copy the function, the train model function from the lab sheet, see if there's an error there. Let's look now. I messed up the batch size earlier. Right. So this finally works. As you can sort of see, the accuracy will be a little random here because you're fine tuning. But after about 10 or so epochs, it should start to stabilize. That's because your feature maps are sort of weird, or are not weird, but they don't exactly match with the kind of data you need initially. The fully connected layer doesn't really have a good have an ideal starting point. But while this trains, there's just one more thing I needed to explain before we move on to the quiz for today. So there is a concept of padding when it comes to CNNs. I will share an image in a moment. Can you see my screen?
Yes.
Yes.
Okay. So let's say I have a 4x4 image and I have a 2x2 filter with a stride of 1. The output should have been a 3x3 image, right? But I needed a 4x4 image for whatever, for either my model constraints, or I wanted to look at these edges more closely, right? I wanted to look at these edges more closely, and therefore I looked at, I sort of like zero padded the rest of it for two reasons. One, now my output size, I can now alter my output size how I want to, and now these edges are represented far more closely because, like, let's say the bottom right element or the A1, 1 element of the filter would never have possibly been able to be multiplied with the 0, 0 element of the input matrix, correct? So to make sure that both these things take place, we can use something called padding. This is same padding. You can also have padding to create, I think create padding which makes it, I don't think you can make it larger, but it depends on the kind of image you have. So if you have a 5x5 image with this and you have padding of 1, I think it'll come out to be um, roughly the you can do the calculations there. That should not be an issue. But that's all. So okay, as you can see, you can see the validation accuracy sort of stabilizing. Um, Probably a few more epochs would do the job. But yeah, that's all the lab has